Swayam Prabha. Digital India. Educated India.
The Laplacian, the number of connected spanning trees, I should not say connected spanning trees, it is already spanning and it is a tree, right. Let me just rewrite it. The number of spanning trees in G is nothing but the determinant of n minus 1 by n minus 1 submatrix of the Laplacian of G. And I should say, of course, my determinant can be negative value. So, we will have to be specific, absolute value of the determinant. Okay. If I get minus 10, then you should not ask how can number of spanning trees be minus 10, right. So, I will just include it here, it is nothing but absolute value of the determinant of the n by n minus 1 by n minus 1 submatrix. Okay. So, this theorem I do not know if how many of you have seen it before, anyone, or if I do not put it in this form, how do you count the number of spanning trees in a graph? Somebody should have heard of this result at least. Okay. If not, this theorem is called as the matrix tree theorem. So, which connects, given any graph, we are talking about undirected. So, I have started here. So, G is undirected unweighted simple graph on n vertices and the Laplacian matrix is what we are going to concentrate, right. And the proof uses the fact that L is equal to Q into Q transpose, okay. And the result says that the number of spanning trees in G, I can count the number of spanning trees that are present in G. It is nothing but the absolute value of determinant of n, this submatrix. Okay. So, I know it is quite impossible to digest suddenly if I say something like that. So, let us go with an example. So, now I will give you a simple matrix, you are going to do the determinant, not cheat me like yesterday. Okay. So, let us just look at this graph G. What is the determinant of this? So, first I have to look at the L of G for this. What is L of G? I always write it in the reverse order, so it is easy for me to write. So, since I said any n minus 1 by n minus 1 submatrix, let us just look at the entry, the submatrix of 1 3, determinant of the submatrix of G by deleting the row 1 and column 3. I just picked it up randomly, it has nothing to do specifically. So, you can just see. So, what is going to be this? I have just said 1 and 3, the submatrix you look at by deleting row 1 and column 3, or if you guys are doing it by any other method is also fine for me, because we also know cofactor of any element is are same, right. So, what is this? Minus 1 2 0 1 minus 1 0 2, right. Is it 8 or minus 8? Sure, right, okay. Because I did not say cofactor, so it is 8. We are just looking at the subfactor. If I said cofactor, then you have to multiply by this minus 1 to the power of I plus j, right. That will also be there as a factor, right. But anyway, we are bothered about the determinant absolute value, so I can just pick this up. So, can you give me the 8 spanning trees of this graph now? So, we expect that there should be 8 spanning trees, that is what the theorem says. So, if that should be true, then you should give me 8 trees out of here. So, then you should give me the spanning trees. So, we are talking about K4 minus E. So, tell me, one of you start listing the 6 trees or 4 trees, whatever you get. So, you want to say this is 1. If I just remove one edge, what about this diagonal edge? It is not a tree. No, he said just remove one edge of the square. So, if I remove, still it is not a tree, right. You should be specific when you say. So, this is 1, 2, 3, 4. This is 1, okay, I will just write all the tree possibilities. This is 1, 2, 3, 4. 8 is there, right. So, all are convinced. Which one did I leave? So, these are the 4 trees which you get by removing the cycles out of it, and you will have the other possibility of all these, I should not say, right. Anything else? I also got only 6 here. Yes. So, then I can just do with what is S and N? That it's sorry. I shouldn't say this, I should say this is my graph, right, 1, 2, 3, 4, and then we have an N, right, yes, thank you. Right. So, we have 8 spanning trees, so at least my theorem says it correct. So, I do not have anything more than that, right, there are no 9, 10 also possible, right. So, this at least gives you a feeling, okay, I can go with this method. If you go into the proof of it, I will not do the proof, you just need to, we have already stated about Q of G, right. For Q of G, we know any submatrix, I mean if G is a tree, then I know that n minus 1 by n minus 1 submatrix is non-zero, right, determinant is non-zero or non-singular, right. So, we can just use that idea here, and we can see that the Q into Q transpose, when we take the Laplacian matrix, determinant exists only when my graph is connected, right. And from this, how many trees are possible is what it says, like if I have a tree, then I know it is non-singular, that means it is non-zero. So, as many number of trees that my graph contains, that would be the value of this determinant. Okay, so, this is how it is getting connected, but to see actual mathematical proof, we have to do a lot of case analysis and we have to see how this comes. Okay, so, that part I will not go now go into. So, now the next step what I want to show you is, it is not only about number of spanning trees that you can talk about. Okay. There is also one more result that I want to connect, we will go into that also. We can also talk about number of spanning forests in a graph. Spanning forests. Okay. By spanning forest, what I mean is, in this graph, there is no spanning forest, right. So far we have talked, that is why I wrote, when I started writing the matrix theorem, I wrote connected spanning tree. Okay. I wanted to say, if I am talking about a forest which is not going to be connected, then I can even count that also. Okay. So, I mean I am not going to do anything big, I just have my Laplacian matrix and I can count only from there. Okay. So, what is the way to do that is, we have already seen the representation, right. Suppose I have the matrix Q and I said this notation I have. So, okay, let me not talk about Q now, I was talking in general for any matrix. We said this notation to mean that I look at the submatrix of M having rows from this set S, right, and columns from this set T. So, what are these S and T? S and T are subsets of the numberings, row numbers 1 to n, or in fact if it is not a square matrix, then I can just talk about in general submatrix, right. So far I did not say anything. So, this is a general notation we have, right, and I also give you one more notation. This is nothing but the matrix of order mod S by mod T, where the rows of this matrix are nothing but coming from the number row labels coming from S and column labels coming from T, right. So, this is the submatrix, we have already defined it, I defined it in the first class if you remember. So, there is the complement of this. Okay. So, the complement of this we will be writing it as with square brackets S bar T, I mean with curly the parenthesis. Okay. For square brackets we use to take rows and columns from S and T. If I am doing it the complement, I just write it as curly bracket. Even in the previous classes I had been writing this, when I write delete row I column j, I just wrote it as A of I comma j, right. So, this is the notation that I am trying to talk about here. So, if this matrix is nothing but the matrix M prime, which has the number of rows to be n minus mod S and the columns to be m minus mod T, where every entry is coming from S complement and T complement. Okay. So, this is what we usually write, even when we write the minors, cofactors, we use this notation. Okay. So, coming back to our definition or the result that I wanted to talk about, consider a set W coming from my set 1 to n, look at the Laplacian matrix L and delete W rows and W columns out of that, and now look at that submatrix, okay, and look at the determinant of that submatrix, right. So, this determinant, okay, it gives you the number of spanning forests in your graph G. Spanning forest on which vertices? On the W vertices, on W number of vertices, right. So, let me give you exact statement for this. So, let W be a subset of this, be a proper non-empty subset, okay, proper non-empty subset of 1 to n, say the vertices, okay. Then determinant of this L of W by W, that is nothing but deleting W rows, the rows labeled with the entries from W and the same columns, right, same columns that we remove. It is opposite to your principal minors. In principal minors what you do? You take, if I say I take L of W comma W, then I mean that I take W rows and W columns and look at its submatrix, look at it as a submatrix, right. Now, what we are doing is we are deleting those W's and then those entries, and then we are looking at the determinant of that remaining matrix, okay. So, this equals number of spanning forests of G, okay, with it just does not say, not only gives you number of forests, it also tells you number of forests with mod W components, okay. If I want 2 component, if I want to look at all forests with 2 components, all spanning forests with 2 components, I just have to remove 2 rows, 2 columns and look at the determinant of it. Yes, when W is equal to 1, I mean when W is a singleton set, then it becomes a matrix tree theorem. It is a generalization of this. So, in which, see, I am not stopping here, it not only gives me number of components in the forest, it also tells me that in which one end vertex is in W and the other end is in complement, okay, in which each component contains one end, one vertex, or I should not say one end because we are talking about vertex, sorry, not edge, sorry, one vertex of W. Okay. Each component contains at least one vertex from W, that is it. Okay. So, this is the beauty that we are talking about. So, if I am saying like if I want a spanning forest containing 2 components, then what I am trying to tell you is if I delete 2 vertex out of it, I will get 2 spanning forests such that one vertex, say W is equal to 2 means, I mean number of elements is 2, then I will have one vertex here, one vertex here coming from W, right. If W1 and W2 belongs to capital W, then I am giving you something more. These are for trees, right, these are components. So, these are going to be T1 and T2 I have. So, that T1 union T2 is a spanning forest. Not only that, I know that every vertex is in one of the components, or I should say each component contains one vertex of W. If I say W components are there, that is the only idea, right. There are W components and W elements are there, means every component has exactly one vertex from the set W. Okay. So, this is a like what to say, a generalization of the matrix tree theorem, okay. And when W is equal to 1, it gives you a tree instead of forest. With one component you get a spanning tree, and obviously we do not bother about which vertex you are taking. So, it contains, it is a spanning tree, right. So, this is another theorem which is also called as matrix tree theorem, I should say matrix forest theorem. It is a generalization of this, okay, of matrix tree theorem. Okay. Now, coming back to my matrix tree theorem, okay, and we had been talking about this determinant, right, absolute value of the determinant of this submatrix. So, what would be the determinant of this n minus 1 by n minus 1 submatrix? So, I will go into that question now. So, we are now talking about the Laplacian matrix, and if I look at the submatrix say of order L minus 1 by L minus n minus 1, okay, I will call it L prime. We know if G is connected, I know this is going, the determinant of this matrix is non-zero, right, and I know it has some value also. Can you tell me what this determinant will be? We can in fact count this determinant, we know it already. So, if G is connected, we know that the spectrum of L, say let me also fix all these things, let our spectrum be lambda 1, lambda 2 up to lambda n minus 1, and we know since G is connected I will have a 0 eigenvalue. I am not talking about multiplicity, let us just list out every possible eigenvalue, right. If this is the case, then what can I say about the determinant of this L prime? So, you need not be even concentrating on expanding the matrix, you know the characteristic polynomial, right. So, now we have a very specific form, I have given you all the details, right. So, what will be the characteristic polynomial for L? where I always find easy route to solve certain things, not dirty my hands. So, I will just tell you here. So, if we are talking about this phi L of lambda as my polynomial, what will be the characteristic polynomial right from here? So, lambda into lambda minus lambda 1 and so on, lambda minus lambda n minus 1, right. So, if I expand this, we have already seen these concepts when we expand this, how the coefficients of a characteristic polynomial will be, right. Not only for adjacency matrix, I said it is true for any matrix, right. The coefficients of the characteristic polynomial, they have a very particular pattern. What is that pattern? Yes, they are sum of the principal minus k of order k, right. If suppose I am looking at any kth coefficient, if I write this as lambda n, say b n lambda power n minus 1 and so on, then I know my b k is nothing but minus 1 to the power of n minus k into sum of, I should write it the other way around, minus 1 to the power of k b k is nothing but sum of principal minus of order k, right. So, now what are we looking for? We are looking for determinant of L prime, that means what? N minus 1 by n minus 1 submatrix, right. And we have already told the fact that if I look at any n minus 1 by n minus 1 submatrix, then the determinants are all going to be equal, right. So, how does this connect with this one here, this statement here? So, from here if I want to look at order k, that means order n minus 1, that is what we want, right. Determinant of L prime is nothing but the n minus 1 by n minus 1 submatrix, right. So, from here if I want to connect that, what will be the value? I have to take, see here when I say sum of principal minus, that is also nothing but we have stated it to be nothing but taking n minus 1, I mean taking k lambdas at a time, you take the product of them and sum it, right. Lambda 1, lambda 2 up to lambda k plus lambda 2, lambda 3 up to lambda k plus 1 and so on. So, all possible combinations is what you do, right. So, if I want to write this principal minor, this can also be written as like sigma 1 phi 1, sorry I should write it as like sigma 1 and so on, lambda k, sigma k, and this 1 to k only I am taking, but we have a bigger expansion for this, right. All n permutations you will look, out of n you are choosing k at a time, right. So, I can just simply write it in another way also. So, choosing k lambdas at a time, you do all possible combinations, sum of all the things, right. K lambdas, product of k lambdas, somebody will scold me if I write here, okay. This is nothing but sum of product of k lambdas at a time, right. Right. So, if I want to talk about determinant of L prime, that means that I am looking at an n minus 1 by n minus 1 submatrix. So, here if I look at n minus 1 lambdas at a time, if I talk about b n minus 1, right, when my k is equal to n minus 1, what will I get? How many possibilities are there? Product of n minus 1 lambdas at a time. There is only one possibility, that is what I am trying to look for, whether you guys have captured that part, right. What is that one possibility? N minus 1, because there is one 0 sitting here. So, if you leave whichever you want to leave, there is the 0 will be included into that, right. So, your principal, in your principal minor, actually you will be taking into account all the n combinations of this product, lambda 1, lambda 2 up to lambda n minus 1, right. you could look into all possible combinations. So, your matrix tree theorem also reduces to the fact that determinant of this L prime is nothing but lambda 1 to lambda n minus 1, right. So, and we will be doing this count. I said we are going to do this over all possible principal minors, right. So, in this part here we would have taken all possible principal minors. So, every principal minor will give you n minus 1 product. So, if you look into that, the number of spanning trees from here can be counted using this value as lambda 1 up to lambda n minus 1 divided by n. The product of all the eigenvalues divided by n. So, this is another result which also gives you a count exactly I can tell you what is that count from the eigenvalues of the Laplacian, right. So, going back to our example of this k 4 minus e, what are the eigenvalues of the Laplacian? We did it yesterday, k n minus p edges we took, right. So, what is the spectrum of this? So, I gave you the answer also there, spectrum of k n minus p edges. If I remove p edges at a time, then we had in general 0 1 and we had n minus 2 occurring p times, right, and n occurring remaining number of times, n minus p minus 1, if we had taken p edges, right. So, now we are only removing one edge from k 4, right. So, since n equal to 4, this value boils down to 2, which appears once, and this will be 4, which is going to be 4 minus 2, right, 4 minus 1 minus 1, which is 2, right. So, the spectrum of k 4 minus e is this. So, from here if I pull out this value, what will be, how many number of spanning trees should be there? So, obviously this 0 is here. So, let me talk from here. So, we have 4 into 4 without counting multiplicities, right. So, I have to write everything. So, there are 2 times 4 is occurring and 1 time 2 is occurring, right. So, divided by 4. So, what is this? 8. So, this gives you, this is what we had already seen also, right. When you took the determinant of the submatrix n minus 1 by n minus 1 submatrix, you got the same value, here also you will get the same value, right. So, you get that. So, this is another way of counting, and if I want to generalize this formula, okay, the one which you guys have all seen, at least I know who have done graph theory, you would have seen this formula. What happens when my g is equal to k n? What is the spectrum of k n? Is it really difficult, guys? Spectrum of k n? Minus 1 and n minus 1, but are we talking about adjacency matrix? Laplacian matrix spectrum we are talking about it. So, spectrum of L of k n is what we have to worry about, right. We are not worrying about adjacency matrix, right. We have to talk about Laplacian matrix. So, the spectrum is nothing but 0 and n. How many times? 0 appears once and n appears n minus 1 times, right, because Laplacian should have 1 0 eigenvalue. How can I miss that? Right. So, now if you put this back into this formula, you will see that you have n to the power of n minus 1 divided by n, right. So, that is going to be nothing but, so from here I will just write it. So, number of spanning trees of k n is nothing but n to the power of n minus 1 divided by n, which is n to the power of n minus 2. What is this formula? Has anyone seen this? Yeah, that is, the formula is called as Cayley's formula, right. When you write degree sequence, that means actually what you are trying to do there is you have a complete graph, you try to list down all possibilities of spanning trees, because there is always edge possible. So, you only talk about rewriting them in listing them down, right. So, this is nothing but our Cayley's formula, which gives the count of number of spanning trees of the complete graph. Okay. So, this formula, I mean this formula is for exactly for complete graph, but this one gives for any graph, right, where lambda i's are the determinant of the Laplacian, right. So, let me just fix it here. So, any doubts in this so far, whatever we have done? I did not do much proof, but if you want I can do the proofs also. History, actually I am not so much aware of it from chemistry point of view, but I have been studying the other parts. Maybe if you have, you should share it with us.
He was actually counting the number of isomers in chemical organisms. That's how he came up with the formula
Yes, I forgot it, but I did read it. I forgot. Okay. Yeah, thank you. Thanks for the reminder. So far whatever we have done and whatever we will be doing for the rest of this week. One book that I mean I follow a lot of books, but you can keep a good reference. If you want a very good mathematical handling of the topic, you can look into this book by R.B. Bapat, Graphs and Matrices. If you are looking for not only about spectral properties, but also other algebraic properties, I would suggest Chris Gotzel, Algebraic Graph Theory. And if you want to read it like a story, you go open Biggs' book. Biggs would have given the whole concept of spectral and algebraic graph theory like a story, bullet points kind of thing, topic wise it will be there, no proofs will be there, but he will hint on the proofs, but not in detail. And these are about mathematical approaches. If you are looking for exactly spectral aspects, only spectral properties, the spectral graph theory is there by Zvetkovich, Doob and Sachs. It is a 3-author book. I forgot their first name, these are their last names. And there is another, Brouwer and Hamas. Spectra of graphs. So, this spectral graph theory, I think this was also called as spectra of graphs. Okay. I do not remember the book title by Zvetkovich. It is also spectra of graphs, right, ma'am? Is it also spectra of graphs or spectral graph theory? Doob, even I do not remember, but one of the two titles you can just see. This is the first book which was published, it came in 1972 I guess, and all these books are a little recent books, the other books are. And for other network theory, somebody was also asking me, you can look into Newman's book, because every network theory will be dealing spectral properties of networks in large scale. So, you can also look into Mike Newman, and this is Introduction to Networks I guess. I am sorry I am giving you incomplete bibliography, I am not giving you year and publishers, I know you people can search it. Spectra of graphs, right, yeah, that is what. Brouwer's is spectra of graphs, that I know. This one I was just I was just doubtful it is spectral graph theory or so whatever it is. So, Introduction to Networks, and there is also other things from genome to social networks. There is also other book from genome network to social networks on network theory. There is lots of books For mathematical handling, you can look into Barpet and Zvetkovich or Brouwers. Godzel, of course, algebraic graph theory, he is also given in detail. Okay. Biggs alone, he has given it like a story. If you are interested to read it like a story, you just take it while traveling in train, you will just read it. You will finish the book in 2 days if you read it. Okay.